Okay, that's good. Yeah, do we have any questions before we start for the day? Okay, yeah, so the test is available. It will be open until Sunday, okay, Sunday midnight. So you should be able to take the test anytime. And the details of the test are already posted on Canvas exam 2 page. Okay, so it will be for, you should be able to take the test anytime. Anytime for 3 hours, and it is proctored by HonorLog. Okay, so that is something you need to remember, and you may need the camera. Okay, same thing, same details as we had for the exam number 1. Okay, so if you face any difficulty there, or if you feel if you feel that there is any picture that is missing, let me know, because that could be there could be some permissions issue. I have tried to fix as much as possible, but then if you face any issues when you take the test, please do let me know. Okay, so that's regarding the exam. And regarding the test preparation, make sure you review the lectures and the slide sets that we have discussed as part of those 2 modules, the synchronization, process synchronization, and deadlocks. Okay, make sure you understand the material well enough before you take the test. Okay, we still have about 4 days to 4 days for it. Okay, and excuse me. Yeah, that's regarding the exam. Okay, so unless you have any other questions, we can get started with the with the today's module. I'm really sorry, I have a sore throat today. Okay, so okay, so that's all about it. Yeah, yeah. If you do not have any other questions, we can get started with this topic. Okay, it's a new topic. We will talk about memory management. Okay, in this one. So let's get started. You see this picture here, right? This is a picture that we have discussed earlier in one of the previous modules. Okay, so it simply shows the let me it simply shows the overall picture, overall block diagram of the system entirely. Okay, it shows the software. It shows the system as having hardware and software, and then we have this operating system, which provides some kind of services to the application processes which are leveraging the hardware. Okay, and if we look at the hardware, we have the processor, memory, and some storage, some attached storage, some other devices connected over networks, and then there are some I/O devices and so on, okay, which are all accessible over the bus. And then we have some controllers for each of those devices. Okay. So we have so this is a picture that we have seen earlier, right? And we have discussed earlier that one of the services that is provided by the operating system is that it allows multiple processes to reside in the memory, in the physical memory at any point in time, such that so that the processor can switch the execution from one process to another process for various reasons, and that context switch can happen quickly enough if we have multiple processes already residing in memory, already loaded into memory and ready to be executed, right? So for that reason, we have for that reason the operating system maintains manages the multiple processes which are already loaded into memory. Okay, and even though we have multiple processes, multiple processes, the address space of multiple processes which is loaded into memory, when a particular process is when a particular process is executing its code, uh, a particular process is not allowed to access the memory locations or the address space of some other process. Okay? And that is kind of that's one of the protections that is offered by the operating system. And similarly, a particular process, it cannot access the address space of the operating system memory as well. Okay? Again, that is all these services are offered by the this kind of protection service is offered by the operating system. Okay? So this kind of isolation is ensured by the operating system. Um, now, uh, now all these um, now all these services, um, all this environment where we have the same physical memory, where we have all these multiple processes loaded into the same loaded into different parts of same physical memory on the system, um, as well as uh, as well as ensuring that a particular process does not accesses the memory locations only which are only assigned to that particular process, and the process is not allowed to access the memory locations which are allocated to some other process. That that isolation, that particular service is offered by the operating system. So it is the job of the operating system um, to ensure that. And to be specific, we have a specific unit which is referred as the memory management unit. And the memory management unit is the one which takes care of these aspects in the operating system. Okay? So that is exactly what we will look at in this particular module. Okay? Now, if you see here, along with the processor and memory, we, of course, as part of the memory, we can store uh, the the data and code that belongs to multiple processes. Okay? So is there any other device that you can see over here in this particular block diagram? Is there any other device where we can store some kind of data that can be accessed by the processor during execution? Or is there any device where we can store some kind of data that can be accessed by the process? Okay. So if you see here, we have, of course, the registers which are located on the processor, right? So we have some registers where we can store a small piece of information, a small amount of data that can be accessed directly by the processor. Okay? So we have some number of CPU registers which are supported it depends on what kind of it depends on what is the processor architecture, which defines how many registers and what types of registers that we can have on the processor itself. Okay? And of course, we have the memory, physical memory, where we store the entire process code as well as data and couple other elements. Okay? Um, for the process which belongs to the process that is currently being executed. Okay? And if you see here, we have some storage, some persistent storage, which is directly attached to the system bus. Okay, and again, we should be able to leverage this this storage space, storage capacity as well, to store some data, and especially to store data in a persistent manner. Okay? And okay, and we have a couple other devices which are a couple other devices on which data can be stored, which can be accessed over the network. Not directly attached to the system bus itself, but accessed over the networks. Okay, so we can have some kind of network attached storage or storage area networks and so on. Okay, which it all depends on the kind of network protocol that we use to access that kind of external storage devices. Okay? And at the same time, we can have distributed systems also, where we can have these processes access data on some other machine which is accessed over the network. Right? So, so all these are different ways in which a particular process can access different can access can have the data available and access during its execution. Okay? So that is just for information purpose, and then uh, we have some input and output devices here, some additional devices. Okay? So these are some additional uh, devices on which data can be stored by a particular process, stored and accessed by a particular process. Okay. Now, now considering that, we if we simply organize them into what we have seen in the previous slide, we have what we call the CPU registers. We should be able to store some data there, and then um, we have some amount of physical memory that is allocated to a particular process, which it can use to store some data, as well as there is um, some persistent storage or some secondary memory locations that the process can make use of to store some data. Right now, if we look at them, if we look at all this, there is some kind of hierarchy that we can see. We have only, because the registers actually reside on the processor, we on the same chip as the processor, um, we have the data in the registers accessible in the same cycle as we can execute the instruction itself. Okay, so the data that is available in the registers is can be accessed in the fastest possible manner. Okay? But however, if you see here, the amount of the amount of data that we can store on the registers is pretty limited. Okay, so and definitely limited as compared to the amount of physical memory that we have available on the system that is allocated to that particular process. Okay, so and um, but if you see here, whenever as part of the instruction, as part of executing the instruction, whenever the processor some needs access to some data which is on the physical memory, it takes a few cycles for it to access that memory. So there is some amount of delay that is involved. Okay, it is not fast enough, not as fast as it can access the data which is already in the registers. But definitely the amount of data that we can store as part of physical memory is more as compared to what we can store as part of the registers. And similarly, we have extended memory, which is both persistent, which may or may not be persistent, as well as um, as well as um, the amount of physical memory that the amount of secondary memory that we can have, whether it is in the form of disks, directly attached disks or tapes, or any other network attached storage. The amount of capacity that we have is pretty high, is several degrees higher as compared to what we can store it as part of the physical memory. Okay, so the amount of storage capacity over here is pretty high, but considering it is accessed over a secondary bus, we this particular the, the data that we have on the secondary memory, that can be accessed at a longer delay as compared to uh, as compared to the amount of time that it takes for the processor to access the physical memory. Okay, so as we move farther and farther from the processor, um, we should be able to um, the process should be able to access larger and larger amounts of storage capacity, but of course at the expense of larger and larger delays. Okay, so for that reason, we should be able to see this as some kind of hierarchy, memory hierarchy, where as we move closer to the processor, the access is faster, and as we move farther from the processor, the amount of storage capacity that is available for the process is higher. Okay, and thereby it is cheaper as well. Okay? So there is one thing that we are missing over here, which is cache memory, and a particular system can have multiple levels of cache memory again. Okay? And we should be able to see it, uh, we should be able to include the various levels of cache into this hierarchy at this point, between somewhere between registers and primary memory. Okay? And again, we can have multiple levels of cache, like cache level 1 cache, level 2 cache, level 3 cache, and so on. Even among them, we can have even among them, the level 1 cache is accessible at a smaller delay as compared to the level 2 cache memory and the level 3 cache memory. Yeah, and similar to this hierarchy, the amount of storage capacity that is available on level 1 cache would be lesser as compared to the amount of memory that we have available on the level 2 cache, and so on. Okay? So that is just for information. So this is some kind of memory hierarchy over here. Okay? So in this particular module, we will be talking about how do we manage the memory allocated to various processor on the physical memory. So we'll talk about that. We'll talk about um, various approaches that are various approaches that are available as regarding the organization of process address spaces in physical memory in this current module. And in the next module, we'll see how we can leverage, how we can extend those services by leveraging the storage capacity, additional storage capacity that we have available as part of secondary memory. Or in other words, we'll see how we can leverage the persistent data storage like disk or tape to 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 support larger number of processes and to increase the overall throughput of the system. Okay, so we'll talk about that as part of the next module, which is virtual memory. Okay. So this is just for some information here regarding the memory hierarchy, and here you can see a picture of a robotic tape library, which comprises multiple tapes, which are handled in an automatic manner by using one robotic arm. Okay, so and each of these tapes that we have as part of this robotic tape library, that will be each of them should be able to support multiple terabytes of storage capacity. Okay? And similarly, it's not just the tapes, but we have the storage systems as well. Okay, and not just the individual storage drives, as you can see here, but we can have multiple such drives managed by uh, uh, placed together as part of a storage server, which are managed by some software which is available to manage the data which is on uh, all these different hard drives, okay, as part of the storage server. So this is one hard drive bay which has probably about 12 or 16 drives here, right? Usually what happens is we have these really large storage systems. Sometimes these storage systems can support about 4,000 of such drives, and each drive can be a couple terabytes. It can hold a couple terabytes of storage space. Okay, so the storage servers can be pretty complex. They can start, the lower level would be about 2 drives or so to support various to offer some kind of additional services like protection and so on for redundancy purposes. So it can start from anywhere between 2 drives to and go on to the extreme level of like about 4,000 drives, hard drives in the same system, managed by the same system. Yeah, and that entire capacity can be available as external storage for a given process, which is um, running on some other system and accessing this storage capacity over network. Okay. Now, if you think about it, here we are talking about a couple petabytes of data, or more probably. Okay. So that is the so we just have this picture here to give you a glimpse of what kind of external storage capacity that can be available um, for an application that is running on some other box. Okay. Um, Now, if you think about it, this kind of storage capacity, we will not be able to provide in the form of physical memory. Okay. So physical memory is always limited and it is definitely difficult to extend, whereas secondary memory is it can be considered as an unlimited storage capacity that can be provided to a process. Okay. Um, so that is something we need to keep in mind as we move to the next module, and we'll talk more about that one at that time. Okay. Do we have any questions here? Okay. Okay. So as I said, in this particular module, we'll talk only about physical memory management. Okay. Now let's get back to that particular topic. Um, Now that we have had a brief talk regarding brief review of what kind of services which are provided by the operating system, especially with respect to memory, and I've also mentioned that we have one memory management unit which is responsible to provide all those different services. Okay? So from that perspective, now that we are talking about designing a memory management unit itself, what do you think are some of the features or functionalities that must be part of this memory management unit? Okay. Um, any idea there? Okay. As I mentioned earlier, there is definitely, as part of physical memory, we want multiple processes to be loaded and, simultaneously. Right? We want multiple processes um, to be loaded and ready to be run in the physical memory, so that the processor can switch the execution for whatever reason. It can quickly switch the execution to some other process, right, without any delay. Okay? So so for that reason, we want the memory unit management unit to support sharing of physical memory among multiple processes. And at the same time, we also want it to provide some kind of protection, um, such that protection service, such that a particular process cannot, even though there are multiple processes loaded in physical memory, a particular process cannot access the memory locations which are allocated to look which are allocated to some other process or the operating system. Okay, so we want it to offer that kind of protection. Okay. And so those are the two important services that we want the memory management unit to offer. Okay, and now if we um, if we simply think about a particular program, right? We have seen earlier that each program has different um, types of data that needs to be stored, right? So it has the code component, a code segment, okay, where its a program is stored, where the program instructions are stored in a specific sequence, okay? And we have the data segment where we store information regarding all these global variables and so on, right? So we have the code segment, we have the data segment, and if you remember, we also have the stack segment where as part of the execution, the process keeps track of the memory allocated to uh, the functions, memory allocated to various functions, and the local um, and the local variables that are declared as part of those functions. Right? And we also have the heap segment where the process allocates memory to the objects which are created at runtime. Yeah. So all those are different segments of memory that needs to be kept track. And if we think about it from the perspective of the programmer would see that each of these pieces of each of these segments is allocated memory in a sequential order. Okay? So so the programmer would see that the programmer would see as if all these different variables or all these different segments are in fact allocated memory, um, right adjacent to each other, as well as starting from the address location 0. Okay, so when so that is exactly what we refer to as logical organization of the or logical address space of a particular process. Okay, so from the perspective of the programmer would see as if all the uh, all the um, variables, or all the segments of a particular uh, process are allocated in an adjacent manner and as starting at the memory location 0. Okay, but as we all know that if we have multiple processes loaded in the physical memory simultaneously, not all there can be only one process which can at max there can be only one process which can be loaded at the memory location 0 in the physical memory, right? So for that reason, the actual physical address space, the actual physical locations where the where the all these different variables and the different parts of a particular process are loaded are not the same as what the are not the same as the logical organization, yeah, or the logical address space of the process. Okay, so for that reason, the logical address space is different from the physical address space, okay? Or the addresses which are seen by the process or the programmer are different from the actual addresses where the corresponding elements are stored physically in memory. Okay, so we have that kind of difference here between the logical address space and physical address space for a given process. Okay, but uh, just take a moment here and think about it as to why why do we need to um, keep track of these two different address spaces, the logical address space as well as the physical address space. So which of them is important to us here? Is there a need for us to consider both of them and keep track of both the address spaces, both the logical as well as physical address space of a particular process? Or is there only one of them that we should be worried about? Okay. Any thoughts there? Okay. So if we think about it, regarding the, as I said, from the perspective of the programmer, we want from the perspective of the programmer, we want the we want the um, we want the programmer to write the program independent of independent of its execution environment, yeah, or the hardware or or the specific hardware on which the program needs to run. Okay? So so for that reason, we also we do not want the programmer to be aware of the fact that there can be several other processes which can be running on the same system. Okay, and of course, the execution of one program must not depend on on the simultaneous execution of some other unrelated process which is sharing the same physical resources, right? Same hardware. So for that reason, we want the independence of which is offered by the logical address space of a specific process. Okay? So we just want the we just want the programmer to think about the various um, to think about to um, so we want the programmer to see the memory allocated to a specific process as a sequential list of as a sequential set of memory locations, okay, and starting from the address 0. Whereas as we know, that is definitely not the case, because that is definitely not the case, and in each process may be loaded at some different part in the physical memory, and uh, and there is and the programmer has no control as to in which part or at which addresses the process will be loaded, okay. And if we and as we know that uh, during the execution of during the execution of these different instructions, the processor would access the data from the physical memory, okay. So during the execution of instructions, um, during the execution of a particular process, the processor must have access to the actual physical locations where the program is loaded, or it must have access to the physical address space of the process. So for that reason, during execution, the physical address space is more relevant. Okay? And considering that we want the user or the programmer to not be aware of the physical location where the process is loaded, we somehow want to convert these logical addresses to the actual physical addresses where the process is loaded, and we do not want the programmer to be aware of it. Okay? So that is one conversion that we need to take care of. Okay, and that is the responsibility of the memory management unit. So it's the responsibility of the memory management unit to convert the logical addresses which are included as part of the program, okay, which are included as part of the program, to the actual physical addresses at which the corresponding segments are loaded. Okay, so that is how both the logical addressing as well as the physical addressing of memory is important. Both of them are important, and we need some kind of mapping among them. Okay, do we have any questions here? Okay, um, okay, so yeah, so this is the memory card. Okay, and on this memory card we have let's say we have the processes. So this is the logical process address space, the address space or the list of addresses that are seen by the process, okay, as part of its code. So what a particular what a particular process um, sees as part of the logical address space is that the entire memory is in fact allocated to that particular process, and it is not aware of any other processes which are loaded on the same physical memory. Okay, and each process also sees as if the address when the starting address of the memory, where the starting of address um, of memory which is allocated to that particular process as starting at the memory location 0. Okay, so so this is how the process sees. So this is the logical address space of a particular process, where it is it is uh, where the various elements of a particular process are loaded into memory, starting at the address space 0, address location 0, and in a sequential manner. Okay? Whereas physically that may or may not be the case, uh, and the corresponding elements may be stored at some other, starting from some other location, as we can see here. And for that very same reason, we need this corresponding mapping from the logical address space to the actual physical address space. And note that there may be some other processes which are loaded at some other locations simultaneously in the physical memory. Okay. Okay. Do we have any questions here? Okay. Yeah. So before we discuss this concept further regarding regarding the various responsibilities of memory management unit, let's look at let's review some terms, okay, regarding execution of a particular program. Okay, so so prior to the execution, we have we start with the source code of a particular program, right? We have the source code, and as part of as a result of compilation, the source code from some high level language, it will be converted to it will be converted to object code, okay? And object code in the machine language, okay? And if you see the specific references that we have in the form of different literals as part of the source code, as part of the program in some high level language, they will be converted to some addresses, some relocatable addresses, considering that the process address space starts at the address 0. So what we have as part of the object code are relocatable addresses, um, and relocatable addresses. And then after the compilation, we have the, as part of linking, what the linker would do is link some additional libraries that are referred by this program. Okay. So again, as part of as a result of this, what we have are again the relocatable object code, okay? Relocatable addresses. And and once we have compiled and linked the entire libraries, we have the complete object code which has the relocatable addresses, and and the object code is ready to be executed. Okay. Now at this point, we have the we have the program, the complete program ready, and that can be either loaded into physical memory, or it can be, or if we do not have sufficient space, or if there is no need to execute the process at the current time, we should be in the program at the current time, we should be able to simply store it as on some secondary memory. Okay? And at some point in time, whenever we have the sufficient memory space available, and whenever there is the need to execute it, we can have the loader program, which would load this relocatable object code into some part of physical memory. Okay? Or in other words, we are allocating some a part of the physical address space to this particular process program, and the loader will load the entire object code as into these address locations, to these addresses. Um, and as part of that loading process, what the loader would do is replace these logical addresses that we have as on in the object code to the physical, to the actual physical locations where the corresponding elements are being stored. Okay, so the loader has the opportunity to convert the physical addresses to the convert the logical addresses which are part of the object code to the actual physical addresses where the which are allocated to that particular process. Okay. Okay, which is what we have here. Okay, so yeah, let's understand that those concepts a little better using one simple example here. Okay, let's say we have a small code segment here, which is part of some program, okay, where we are declaring one one variable. Okay, over here one global variable, and then we have one parameter that is being passed. There is a definition of this method that we have here, and then there is a local variable that is being created. Uh, Excuse me, we are making an assignment here, okay, for that global variable, and we have a method call here. Okay, so let's say this is the small code segment that we have. Okay, and so that is the high level language. So this is the high level language. So this is available in some high level language. Okay? Now, after compilation, we will have some kind of object code, relocatable object code in this particular manner. We have a here we see one code segment and one data segment. Data segment is where we have allocated the space for that gvar variable, okay? And that is the corresponding address. Okay, and as part of the code segment, we have couple lines of code. So this is converted to some object code. Okay, and we have and we are making some function calls, and we have the definitions for some methods and so on. Okay? And if you see here we are talking about um, here we are trying to access the gvar the value which is there in the here we are trying to access the memory location which is where we are storing this particular value for this variable. Okay. If you see here, the corresponding address where the gvar where the value for this variable is stored is 0036, and that is exactly where we are storing this value number 7 over here in this particular instruction. Okay, okay. And okay, and so on. So you should be able to read this object code later. But one important thing to note here is that we is that if you see the relative address at which the the addresses that we have here, they show that the address space starts at address 0. Okay? So the location, the logical, so this is the logical address space, and it is starting at the address 0, as we can see here, and we have the corresponding elements stored at different uh, memory locations starting from the address 0. And if we can see here, um, all the elements are assigned the memory locations in in an and in adjacent memory locations. Okay. So so this is a part of the object code, and the addresses that we are seeing here, they are logical addresses, or they're relocatable addresses. They're not the actual physical addresses where the corresponding elements are stored. Okay. Um, so that is something that we need to understand, and then at some point in time we have let's say uh, this particular program, uh, it also needs it also refers to some libraries, and then we have the linker which would combine which uh, would combine the object code of the libraries that are referred. Okay, and if that is the case, then again, as part of adding those new modules, new new libraries, the addresses that are addresses where we have those the actual address locations would again change for the process. As you can see here, we have the variable stored at 0136 instead of 0036, and we have the corresponding and it uses the corresponding addresses again. Okay? And so on. So but if you see here again, the relative address is still 00. Okay, so so the over here again, if you see the what we have as a result, again after the linker adds those additional libraries or the additional modules that are being referred to, we again what we have are the logical addresses, or the uh, yeah, so what we have are the logical addresses, or the relocatable addresses. Okay, but at some point in time, this object code, it needs to be loaded into physical memory so that the process can be executed, and the corresponding elements can be accessed by the processor. So that is So that is done. So if that is done at the time of loading, then if we see here, the process is being loaded at the address 4000. Okay, so starting from the address 4000, we have all these different parts of the process loaded in a sequential manner in this particular example. Okay, and if you see here, the actual address where this gvar variable value is being stored is 7136, and that is exactly what we are accessing here. Okay? So these are the actual physical addresses. Okay? Assuming this program is being loaded at the address starting from the address 4000. Okay? And these addresses are referred to as the physical addresses, and these are also referred to as the absolute addresses. Okay? Not the relocatable addresses, but the absolute addresses. Okay, so that's the difference between absolute program and the relocatable object code. Absolute code and the relocatable object code. Relocatable object code is where we have the logical addresses included as part of the object code, whereas the absolute code is where we have the absolute physical addresses where the program is loaded. Okay, so that's a small difference. And if we see here, so this is basically a summary of it's basically a summary of what we have discussed so far. So we have the source program, and and then after compilation, what we get is the object code. Okay, object code with the relocatable addresses probably. Okay, we'll talk about that. But as a result of compilation, we get the object code, and then linkage editor would combine some other modules or other libraries, and we have the module ready to be loaded with all the required components. And at some point in time, the loader would physically load the entire program, entire object code into physical memory. Okay, and then we have the in-memory image ready for execution. Okay, so this is just a summary regarding the entire procedure to which is which is part of preparing a particular program for execution. So those are some terms. Now that if you see here, as I mentioned earlier, we for a particular process to be executed, what we need are the actual physical addresses where a particular say variable or some segment is stored, right? And logical addresses cannot be used by the processor. So for that reason, what we need is the absolute code and not the relocatable object code. Okay, we do not need the logical addresses as part of the code or the instructions that will eventually be executed by the processor. What we need are the physical addresses. Okay, and that can be done at each of these three situations. We should be able to we should be able to replace the logical addresses, and we should be able to replace the logical addresses with the physical addresses during the compile time or during the load time or during the execution time. And the example that we have seen here is where we are replacing the logical addresses with the physical addresses in each of the instructions during load time. Okay, so during load time, we saw that the program is actually loaded at this particular physical memory location, starting from 4000. And based on that, we have identified based on that, the loader has identified the actual physical address for that gvar variable, and has replaced that logical address with the physical address. Okay, so this is an example where the loader has replaced the logical addresses with physical addresses, or in other words, the loader has performed the binding of logical addresses to the actual physical addresses during load time. Okay, okay? So this is the example that we have seen. At the load time, the loader has performed the binding of physical addresses to logical address, the logical addresses to the actual physical addresses. Okay, but if for whatever reason, if there is a possibility that we have the information regarding the exact location where the program will eventually be loaded into physical memory. If we have that information during compilation time, then we should be able to perform that conversion, perform that binding, or replacing the logical addresses with the physical addresses that can be performed during the compilation time itself. Okay. So that is another option, and the third option would be simply delay that binding, delay that conversion until the actual time of execution, until each instruction is being executed. So what happens is the loader would simply load the program with the relocatable addresses or the logical addresses, and during execution, whenever the process is, whenever the CPU is executing a specific instruction, if it sees a logical address, then the memory management unit will interfere, and it will make that conversion in line as part of the execution of the instruction. It will first convert the logical address which is there as part of the instruction to the actual physical address at which which is corresponding to that logical address. Okay, and then the instruction is executed after the replacement. Okay? So that is another possibility, which means that the binding of logical address space to the physical address space, it is being done at the execution time or at the runtime. So these are um, three different ways in which the binding can be done. Okay, do we have any questions here? Okay, yeah, so this is basically the summary of what we have just seen. The address binding, it can be done either at compile time or load time or execution time. Okay, now as I said earlier, if we know the physical memory locations where a program is going to be loaded, for sure, um, then if we know that information a priori or during the compilation time, we should be able to include the actual physical addresses itself, and we can have the absolute code ready and not the relocatable object code um, right at the time of compilation or right after the compilation. Okay? But if we do that, note that at this point in time, but if we perform such an action, um, if we perform such an action, the absolute code, it has the actual physical addresses. And if for whatever reason, if we are unable to load the process later on during execution, if we are unable to load the program at the exact same physical uh, starting from the same physical memory location, then because we have the physical addresses as part of the object code, we need to recompile the entire code if we want to eventually load the program at a different location in physical memory. Okay, so that is one of the limitation with this particular approach. So that's one of the limitation. And then if we uh, uh, as we have seen in the previous example, we can also perform this binding during load time. Okay? So we have the relocatable object code, and as part of the loading, we know the loader would know exactly at what location at what memory location the program would be loaded, the program need to be loaded, right? And based on that, it should be able to perform the binding from logical to physical addresses. Okay? Again, if at some point in time, if here with this particular approach, one of the limitations is at some point in time, if the program needs to be if the amount of if the set of addresses which are allocated to the process, if they are not sufficient, if there is a need for the process to grow beyond that, and if that is the case, then again we need to reload the entire program starting from a different address. Okay, so that is one of the limitation with this particular approach. Okay, but an advantage over here with these two approaches, either compilation performing the binding at either the compilation time or the load time, one of the benefit with these two approaches is that the code that is loaded into uh, into physical memory is the absolute code, or in other words, each instruction has the actual physical address of each element that it will be accessing, right? So 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 when a particular so when the CPU receives an instruction for execution, it already has the actual physical address from where it can access the corresponding data element. Okay? Uh, but that is and for that reason there is no additional delay that is involved. Yeah, but that is definitely a shortcoming if we delay the binding of logical to physical addresses until the execution time, because if we perform that binding at the execution time, the the instruction will include the logical address and not the physical address. And then as part of execution of each instruction, each such instruction, the memory management unit need to perform that conversion, that translation from logical address to physical address space, and only then the actual instruction can be executed after fetching the data from corresponding memory location. Okay? So that definitely adds some delay at runtime. So the user should be able to perceive that delay as the execution delay of the program, okay? Which is definitely not the case with both compilation time binding and load time binding. Okay? Um, Now that delay, it can be um, it can be reduced by adding by having some kind of additional hardware to perform that mapping, okay? And by making use of some additional registers like base and limit registers and so on. Okay, but in spite of that, there is this additional delay that will be included if we perform this binding at execution time. Okay, now that that is the shortcoming, but do you see any kind of advantage or benefit by delaying the binding until execution time or until the runtime? Is there any reason that we are really talking about this one and not just these two? Okay. Do you have any ideas here? Okay. Um, so I said that if for whatever reason the the process needs more memory during runtime, okay, and if there is a need to extend the amount of memory space which is allocated to a particular process, if we perform the if we perform the binding either at compile time or at the load time, we need to either recompile or reload the entire program if the starting address changes. Okay, and and that will have some impact, and it may not be even feasible it may not even be practical for all possible applications. Okay, but that is something that can be that is possible if we perform the binding at execution time, because as part of because as part of this particular approach, we perform the binding, or in other words, we do not perform the binding until an instruction is executed, or until a particular um, a particular address is a particular logical address is required to be accessed as part of execution of some instruction. Okay, so for that reason, we should be able to allocate the memory at any part of the physical memory, and if we have the corresponding mapping information available, between the logical address and the physical address. So that actual binding, the conversion can happen right at the time of executing the instruction, and thereby we have that kind of freedom or independence uh, to place or to change the location of a particular element at any point in time during the runtime, during the execution of a particular process. So that is the advantage that we have with binding at execution time. And for that very same reason, we prefer to perform the binding at execution time and not compile time or load time. Okay, and we'll also see in the future sessions, we'll see how this one will be even more beneficial, okay? In spite of having the additional delay that is introduced by runtime binding of addresses. Okay. Okay, do we have any questions here? Okay. Um, so as I said, it is the um, as I said, if we are performing the binding at runtime, it is again the job of the memory management unit to convert the given logical address to the physical address space. Okay, so so if the CPU encounters a logical address as part of executing a given instruction, it provides that logical address to the physical address space, and it provides the logical address to the memory management unit, which would convert it to the corresponding physical address and fetches the corresponding element from physical memory. Okay. Okay. So that's the difference between logical and physical address spaces. Okay. And as part of this conversion, the memory management unit, it uses one simple solution is for the memory management to use what we call the relocation register. Okay. So what the relocation register gives is the starting address where the process is currently loaded. Okay. So if the so as we have seen earlier that the logical addresses of a particular process, they start at the address 0. Okay? So given a logical address like this, say 346, the memory management unit, it converts it to the physical address by using the value that it has, the starting address that it has, which is loaded as part of which is available in the relocation register for that specific process. And then you should be able to compute the physical address location corresponding to this logical address location. And then should be able to fetch the corresponding element from physical memory. Okay, and if you see here, this relocation register um, is very specific. The value in this relocation register is very specific to each process, right? So we can have multiple processes. Um, we can have we can have multiple processes loaded into different parts of physical memory, and each process may be starting at some specific address, right? And if we can have that starting address, we should be able to convert the logical addresses of any such of any process to its own corresponding physical addresses. Okay? Um, so for that reason, this relocation register, the starting address of the set of memory locations allocated to a particular process, that will again be stored as part of the process data structure. Okay, so that is one small thing that we need to remember. Do we have any questions here? Okay, so this is one example of runtime binding, okay, using a relocation register. Okay. Just some other simple concepts that we need to be aware of as we discuss further topics. Okay, one of them is dynamic loading. So far we have been talking about having the entire process, entire code belonging to a specific process um, in memory loaded as part of the loading process, right? So but it may not always be, it may not be required at all times. Uh, so, so for that reason, here what we are looking at a concept called dynamic loading, where where the entire code that belongs to a particular process is kept on disk in a relocatable loading format or having relocatable addresses. Okay, and the routines are not loaded until it is referenced. Okay, a particular routine is loaded only when it is referenced or only when it is called, and thereby we have only the required number of routines or required routines in physical memory. And thereby, we should be able to make better use of the available physical memory space. And as it is obvious, this is especially helpful when we have large programs which have infrequent, which considers a lot of cases where a lot of special case scenarios where we which may not occur pretty often. Okay. So if that is the case, then we may not need to have the entire program in physical memory at all the times. Okay. So yeah, so this is the concept of dynamic loading. Okay. And this can be, we do not really need any additional support from the operating system towards this, and this can be done by using some programming libraries. Okay. So this is a concept that we need to be aware of, but it is but not from the perspective of operating system. And similarly, we have another concept which is dynamic linking. Okay. So the concept that we have seen earlier is where we are linking some additional modules or additional libraries which a particular program is accessing, right? So we have seen that, and um, now similar to now uh, there may be a situation where we have multiple programs accessing the same set of libraries. And if that is the case, if we perform the normal static linking, we should be, we may end up having a copy of those entire libraries as part of the address space of each process that is loaded into memory. Right? Now, obviously, it is not quite efficient, especially with respect to physical memory utilization. Right? Instead, what we can do is we should be able to load it in only one part of the memory, and dynamically link it or access those um, locations, memory locations, physical memory locations where the libraries are placed. Okay? That is referred as dynamic linking, um, where as part of linking, we, instead of actually including a copy of the entire library modules as part of the address space of each process, what we do is we simply include what we call a stub. Okay. um, which provides us the uh, which provides us the memory location where the corresponding library modules are loaded in physical memory. Okay. And so stub is the one which would help us help us in locating the library routine uh, in memory. Okay. And whenever it is referenced, the stub would simply replace itself with that particular address, and that specific routine is called and executed. Yeah. And this particular approach is especially helpful when we have read-only libraries. Um, and and Yeah, especially when we have shared libraries. So we should be able to make better use of the physical memory space by not replicating the same libraries in the address space of multiple processes. Okay. And at the same time, if we have if we have multiple versions of these library modules, then we should be able to, then it will be easier if we have the corresponding stub to simply replace one version of the library with a different version, and that can be done again at runtime. So those are some benefits of having of considering this particular concept. So these are some aspects that we need to understand before we move further. Do we have any questions here? Okay. So let's stop at this point, and then we should be able to continue this in the next session. Okay. Okay. You all have a good weekend, and we'll meet again. Thanks.